Do your intro. All right. Thank you everyone for joining us for this webinar, History of Audio Technology, presented by Peter Moses. My name is Laura Lawrence, and I'm the Global Marketing Director at Harman. Just a few things before we get started. Everyone on the call is muted to keep down noise levels during the webinar. However, there is a Q&A function where you can submit questions to the presenter, and he'll try to answer as many questions as possible at the end. The webinar is being recorded, and the link will be made available a few days after the presentation. We do have a number of other webinars taking place over the next few months for audio, lighting, video, and control, and we'd like to encourage you to take a look at the different webinars in our Learning Sessions workshop series on pro.harman.com. We're adding new sessions daily and have over 20 sessions scheduled for August and September, so watch for those on the calendar. And now I'd like to introduce you to my colleague, Peter Moses, the presenter for today's webinar. Peter is a 20-year veteran of the audio industry with experience in large-scale projects for universities, studios, houses of worship, and mass transit systems, as well as multi-platinum engineering credits with clients such as will.i.am. Now I'll pass it over to you, Peter.
Thank you so much, Laura, and thank you to everyone for attending this webinar. This is something that I've been very passionate about for a long time, and I'm very excited to bring it to you. Before we jump into today's webinar on the history of audio technology, I'd like to take a minute and talk you through why I believe some of the things we're going to touch on today are so important. So if we actually have a look at what we're going to cover in the next half an hour to 45 minutes, it's going to be an understanding of microphones and their evolution. Who were the actual people behind inventing the microphone, and why was there a need for it? Very similar thing with the speaker, both devices, of course, being transducers, devices that convert one form of energy to another. In addition to that, we're also going to look at recording. What was the need to actually record audio, things that we take for granted today? Where did that come from? Who were the brains behind this, and how on their journey did they achieve the goal of being able to permanently record audio? From there, we look at amplification and how do we actually turn something up? How do we turn it down? And how does that then have an impact on the other components in the signal flow chain? How can we then record something that has been amplified? Did it need a different type of recording medium, or could it use the same one that they were using beforehand? All really interesting points. From there, we look at tape recorders in depth, the story around who invented them, why they were invented, and again, not just the invention, but then the actual advancement of technology through the years. Some really exciting and interesting stories there that take their lead from not only wartime inventions, but also tinkerers such as myself. Not that I invented a tape machine, but again, people who love playing around with soldering irons and components and getting a good understanding of how electron flow can be captured. We then move into processors, things such as dynamic processors. Many of us are very familiar with the term limiter or compressor or even equalizer, but who were the inventors behind this technology and what was the need? Again, we understand that a lot of inventions come from an actual need. So what was the spark? What was the light bulb moment in certain people's heads that allowed them to come up with these devices? We then move into mixing consoles, which takes a large portion of all the early invention stories and dives and puts them into the one melting pot. From there, we look at some really cool stuff, a bit more contemporary, digital audio and digital audio protocols, and we finally finish up with a few historical figures. The goal of today's webinar is to really ensure that at the end of our journey, you have a good understanding of the basic key figures behind some of the innovation that leads to many engineers, live musicians, audio-visual practitioners, broadcasters, and other industries' ability to work in technology that has been invented by certain key figures. A really cool adventure, and I'd like to invite you to now join me as we jump right in. So before we go into the actual story of who, how, what, and why, let's look at some basics. And you can hear a kookaburra going off in the background. I apologize for that. My noise cancelling kookaburra algorithms are currently not plugged in. So we have audio. And the world of audio really is a complex one. It's one that not only interprets acoustic energy, sound, air moving back and forth into electron flow, but it's one that takes a number of different paths where we can amplify, we can store, we can recreate audio. So understanding the basics of what audio is, I feel, is really important. And summarized in a very brief way, audio is represented as electron flow in a number of circuits. It is alternating current electron flow, which means it changes polarity between positive and negative. This is really important to understand because all the inventions we discussed today basically rely on this principle, a really unique feature of what we're talking about. So audio electron flow actually travels through a conductor, copper cable. Now, anything that can conduct electricity can indeed conduct audio at different speeds, at different quality. For the most part, when we're transmitting audio, electron flow representing audio, we're transmitting it through copper. Copper cables, copper circuitry on a board, all very similar, but all very important in terms of getting audio from A to B. This is really important to understand because if there is a break in the circuitry, if there is a break in the copper trace or in the copper cable, audio does not flow. And if audio does not flow, we are without audio. Now, this is important to understand because in each one of these inventions, there were a lot of struggles, a lot of challenges, especially in the early times of making sure we had good conductors, good copper that was able to transmit electron flow as audio. So when we look at this, we look at some of the key inventors. We look at people that were looking at how do we create sound, which is basically air moving back and forth, into audio. How do we change that energy and how do we then represent it? How do we get electron flow moving along this copper to create audio? And some of the key people in it are on this slide right now, and we're going to delve into that in the coming slides and get a good appreciation of some of the challenges they faced. A really important note about today's presentation is that we're only going to touch on certain key figures, but that does not mean they were the only exclusive people working on it. One of the staples of creativity and innovation is that a lot of times multiple people will be working on technology separate to each other at similar times. So we definitely acknowledge certain key inventors along the way, but understand there are a lot more that we're probably not going to touch on today. When we look at innovation for audio, we basically cut it into three groups. The early group, the transducer technology, taking sound into audio, things such as microphones. We then look at recording, so actually capturing that electron flow, which is magnetic tape, and in later years, digital audio technology. From there, we look at speakers, which again is another form of a transducer. This time, taking audio and reproducing it back into sound, so creating unique air movements once again. And as you'll see in this next slide, it's those unique air movements that basically allow us to build a whole industry and career around. So let's just delve in and have a look at those air movements. When a vibration occurs, sound, as we know, compresses closer together and further apart. Now, when the ear actually hears this, a really cool thing happens. The little hairs within the inner ear, the stereocilia, convert this air movement into electrical-like messages going to the brain. This is how we process sound. This is how, as humans, certain sounds can evoke certain emotions within us. Happiness, sad, being a bit edgy, especially if we're watching a horror movie, or anticipation. So looking at this, understanding the basics now of sound versus audio, sound being acoustic, audio being electrical. Let's look at some of the key figures behind putting this technology together and ensuring that we could capture and reproduce sound. One of the early figures in terms of actual transducers, taking air moving back and forth and turning it into audio, was Johann Philipp Reis. And with his Reis telephone in the mid-1800s, he was actually able to create a transducer that took acoustic energy and represented electron flow on the other end. Now, the unique thing about this is while it's widely believed this was the first transducer invented, it's not actually commonly known that although it was a transducer, it could not reproduce actual complex audio waves, what we're used to hearing all around us, be it birds chirping, be it someone speaking, or even a menagerie of different sounds such as drums, music, city lights, traffic, all that stuff. All it could do was basic tones, and we see those basic tones in the red, the blue, and the green waves. So really unique tones that were able to oscillate quite regularly. His transducer was able to convert that energy. But when we look at an actual complex wave, which is the black wave, something that has a really unique attack, decay, sustain, and release, the Rice transducer was actually not adequate to be able to do this. So although this technology was around in the 1850s, the 1860s, we were not actually reproducing something that humans would associate with common audio, common sounds around us. That was then improved on by Mr. Bell. And what Mr. Bell was able to lead us to was a transducer that could now reproduce complex waves. It could understand what was coming in, reproduce that electronically as an electron flow. And from there, we actually had a speaker on the other end giving us a very similar sound to what was being reproduced at the transducer end, the microphone end. Now, what's unique about this is the early inventions around this were all driven around communication. So we're talking about telephone communication systems. We're talking about very, very short lengths of communication. But again, being able to transmit messages from one location to another electronically. So really unique. I dare say that when people such as Rice and Bell were making these innovations, they had absolutely no idea how they would change the world and where they would lead to. Now, an interesting point here is if we jump forward about 30 years, we go to about the 1910 stage, and a young gentleman in the United States of America, James B. Lansing, started experimenting and innovating with his own transducers. And of course, the shirt I wear today and the company I work for, Harman, has a brand that was started on the back of James B. Lansing's innovation, of course, being JBL speakers. And James B. Lansing and his story around transducers is a really cool one that we're going to dive into a bit later on in this presentation. As we loop back now, we have a look at the basics and understand that Rice and Bell came up with some really unique innovations around transducers. But at this stage, all you could do was convert acoustic energy, being sound, into electron flow, being audio. There was actually no way to record this. There was no way to capture this and replay it at a later time. So let's just think about that. When we're talking about a piece of music, you actually could not hear a piece of music recorded. The only way to hear a common piece of music was to attend a performance, or perhaps if you were a pianist or a violinist or a musician, you could buy the sheet music and play it at your leisure, learn it and play it at your leisure. There was actually no way to hear recorded audio all the way up until the 1880s, which for me, I feel is still, not too far back in history. So there were many innovations around this time, not only in the US, but also in Germany and the UK, that were looking at how we could capture electron flow and store it and then reproduce it at a later time. The story that really sort of jumps out to me is the story of Thomas Alva Edison. Not only was he responsible for innovations such as the modern light bulb and other electronic innovations, but Edison was also absolutely taken by how we could permanently capture and replay some audio. This led to his innovation of one of the earliest forms of recording, the Edison wax cylinder. Now, the unique thing about the Edison wax cylinder was that a lot of his early innovations were successful. He was actually able to record electron flow as audio. Upon replaying it, what actually happened is his device would ruin the grooves that were created when recording. So he'd end up with replaying something that was perhaps not as accurate as what he had hoped. Over time, he mastered this and came up with the wax cylinder. And the wax cylinder was the first, I would say, commercially available product that allowed us to not only record but also reproduce audio. And I think that's a really cool invention. In fact, as an audio engineer, I think that my whole career is based on this one innovation as well as others around it. Now, what's unique about this is my favorite photo of Edison. It shows someone who is to some extent frustrated, someone to some extent who has experimented time and time and time again. And we're all very familiar with the famous Edison phrase around innovation. The unique thing about this is that although Edison came up with the wax cylinder, that was the spark that lit off so many other inventions. And their inventions we're now going to look on. They're inventions that the audio engineering and associated career paths were all built on. So we understand the basics of transducers and their invention story. We understand the basics of recording and that innovation story. But indeed, what then led us to where we are today? Well, it's my belief, having spent perhaps an unhealthy time pondering this over the last decade or two, it was amplification. At this stage, we could not turn the electron flow up. We could not turn the audio up and make it louder. We also could not turn it down and make it softer. That did not happen until the turn of the century, and Dr. Lee DeForest, who is quite a character himself, came up with the Audion valve. Now, Lee DeForest's Audion valve was itself an innovation on earlier technology by people such as Fleming and Edison. It took into account things such as the light bulb and really was a unique invention around how do we add more electron flow to the existing audio path? How do we create a bigger representation of what is already there? And Lee DeForest's adventures led him to come up with this, the Audion valve. Now, the unique thing about the Audion valve is that it would transmit electron flow representing audio through it as alternating current. That electron flow then hit a grid. Now, this grid almost acted like a door that turned on or off, open or close. If the grid closes, no audio passes through. But if the grid is totally open and the heater under the cathode where the electrons sit is totally charged, then it creates an environment within this vacuum where added electrons from the cathode will now jump across the grid onto the plate. That unique phenomenon happening creates larger amounts of electrons flowing through the Audion valve than were present at the input. Because of this, we had more electrons leaving, representing alternating current, representing audio. By controlling this grid, and by something as simple as having a potentiometer, a pot, or what we call a knob, turning and controlling this grid, we then end up with what you see on the screen at the moment. We end up with amplification, the ability to turn audio up, increase electron flow, or indeed turn audio down and decrease electron flow. This is really unique, as this invention late in DeForest's career really cemented him as a global innovator and somebody who contributed greatly to the story of electronics moving forward. Of course, DeForest and his contemporaries' invention was not limited to the world of audio, but again, considering that I'm an audio person and someone that's almost audio mad, if not mad altogether, this is really what we're focusing on today. Now, the unique thing, looking at these slides, we see some of the very early Audion valves and indeed Audion valve circuits. What's unique about this is these circuits were built by hand. These components, a lot of times, were machined by hand. And because of that, in the early times of operating these components, we would get a high failure rate. Because of this, there was a large demand for people who actually understood circuitry and were able to maintain these components as they were being operated. And that was a story that lasted from the turn of the century all the way up until the late 1960s. And it's a theme that we will see revisited time and time again. So before we move a bit further into amplification, let's just look back on some of the key figures. It was not only De Forest's Audion valve, but earlier work by Jack T. Fleming in the UK, and indeed people such as Edison before them, that contributed to this one breakthrough, the ability to control electron flow and add electron flow, the ability to turn things up. So I dare say without these innovators, we would have no classic lines from the movie Spinal Tap. Now, what's unique is from the turn of the century up until about 1950, vacuum tubes, the Audion valve, were the main form of amplification, especially within audio circuits. Something happened though in the 1940s, and that something was three physicists at Bell Laboratories getting together and coming up with the transistor. The transistor changed modern electronics and indeed changed the audio world significantly. How did it do that? Well, similar to the vacuum tube, the transistor also had three key compartments. It had the emitter, the base, and the collector. And using these three components as part of the one device, we had the same principle. We were able to then increase electron flow or decrease electron flow. Instead of jumping over a grid this time, electron flows were making their way through depletion regions within transistors. The unique work of these three physicists at Bell Laboratories earned them a Nobel Prize. So there is no doubt that the significance of this innovation, not only for the audio world, but the external everyday world, was huge. Early transistors looked like something that basically came out of science fiction movies. They were big, they were gelled together, they were unique, they were fused. They were these really cool looking components. And it was not long before the audio world were able to integrate transistors into their own designs. The next slide shows the AKG C12, one of the world's most popular microphones, a vacuum tube microphone. The picture to the right of it shows the AKG C414, one of my favorite microphones. And the C414 is not only different in physical size, but also different in the way it's made up. And of course, that difference is it uses a transistor as opposed to the vacuum tube. The fact that it uses a transistor means that physically it is a lot smaller, it is easier to navigate, but also it sounds very unique, very different. And I actually don't think we've got time to get into the positives and negatives of transistors versus vacuum tubes from a sonic characteristic point of view. And there are a lot of amazing arguments on both sides of the fence, no doubt about it. But what's really unique about looking at this history of audio and this evolution piece is that indeed we went from really large components that were required because of the vacuum tubes and the amount of electron flow required to power the vacuum tube, all the way through to much, much smaller devices and smaller components due to the innovation of the transistor. And of course, over the years, the components themselves, not only vacuum tubes, but also transistors, became smaller, became more refined. And it is a reality that we still use vacuum tubes today. They're in some of my favorite audio circuitry and guitar amps, but we do use a heck of a lot more transistors. And that just comes down to ease of use, obviously manufacturing costs, and also reliability. The need to have staff on site regularly to maintain vacuum tube circuitry is not as high when you're using predominantly transistorized circuits. We find ourselves in the 1950s and say, okay, we've got a good understanding of the basics of audio transducer innovation. We've gone through the basics of amplification from vacuum tubes all the way to transistors. But what actually happened to the speaker? Were there any innovations during this time? Did it get better? Did it stay the same? Did it possibly get worse? Well, luckily for you, I have those answers. Now, of course, the speaker did improve over time. And while there were many different companies improving the speaker performance, it makes the most sense to talk about what James B. Lansing was doing and his journey of the speaker. By the 1950s, James B. Lansing found his ultimate transducer, the JBL D130. This speaker was used in a range of different applications, from movie houses to recording studios to, of course, early home theatres. However, the JBL D130 is perhaps most famously known for its use in Fender guitar amplifiers. So prominent was the sound of the JBL D130 that Fender advertisements of the time boasted its use within these components. For me, I find this to be a really cool feature, and understanding that today, as a multi-million-dollar professional and lifestyle division, JBL speakers actually add to the experience that millions, if not billions of people are having around the world. And it all started back in the 1920s. So let's dive back and have a quick look at the journey of James B. Lansing and how we ended up with the JBL brand that we know and love today. So James B. Lansing was toying around with speakers at the turn of not long after the turn of the century. Definitely by the 1910s, he was experimenting with transducer technology. By the 1920s, James B. Lansing started the JBL Sound Company, the James B. Lansing Sound Company Incorporated. This famous building was in Los Angeles, California, and it was a building where all parts of the transducer were actually manufactured on site. This is really unique in a time where we find a lot of components are borrowed, used, innovated time and time again. James B. Lansing actually had a team carving these components out by hand, and I think that is really unique and really cool. One of the great stories around this time is that a very young Les Paul, who was not only an innovator electronically himself, but as we all know, one of the most famous icons in contemporary music and obviously contributions to the electric guitar. Les Paul visited the James B. Lansing Company, actually walked in, had an appointment, sat down with James B. Lansing, had a listen to the speaker, gave some of his honest feedback, and James B. Lansing, having heard that, said, let's go to lunch. Now, this is really unique, and this is a story told in John Earle's book around the history of JBL. But what is so interesting about this, we will learn in the upcoming slides. Between James B. Lansing and Les Paul, the circle of friends that they shared, or innovators that they shared, led us to a number of solutions that we use today in the professional world of audio. So let's go in and have a look at that. We'll take a slight detour and look at, okay, transducers have now come forward in the 1950s. What has happened, I should say, with magnetic tape recording? So Edison's wax cylinder evolved into different mediums and different formats that we were able to record more electron flow onto. Vinyl record was one of them, as were some early tape methodology and different types of tape. So not the tape that we think of today. But in the 1940s, a US-American scavenger operating in Germany, Jack T. Mullen, found some amazing magnetic tapes in the field. And he was absolutely amazed because the quality of the tape and the build of the tape led him to believe that this tape could indeed be the tape that he heard being broadcast by Radio Berlin. Long orchestral performances that at the time Mullen believed the orchestra to be live, because the performances were going well over 100 minutes, well over what was normally being recorded on the mediums of the day. As Mullen made his way back to the United States, he was able to confirm that indeed was the case. And he took his discovery of magnetic tape to people such as Murdo Mackenzie and Bing Crosby at the time, and enabled them to look at how they could formulate a solution that would result in such a tape. By putting together a solution that resulted in the manufacture of magnetic tape in the United States of America, they now were able to change the way they did business in the entertainment world. In particular, they were able to change the way they recorded shows and performed shows on the radio. Up until this time, long-running shows had to be performed live. It was almost impossible to record a long-running show on a physical medium because that physical medium could not store that amount of information. Murdo Mackenzie, Jack T. Mullen, and their associates were able to come up with a way to form different types of carbon, different types of PVC together to capture electron flow, great amounts of electron flow representing audio, large amounts of dynamic range, and they were actually able to do that and replay it time and time and time again with little degradation. This ushered in for us the era of the magnetic tape recording, and it's there that Les Paul also contributed with his sound-on-sound methodology, enabling us to record more than one or two unique sounds at the time. Now, looking at recording magnetic tape, playing more magnetic tape back, how do you actually get sound onto magnetic tape? And again, it's something that was done through audio circuitry, through a number of different pioneers. And one of those pioneers, again, was Les Paul. And I promise you that this is not the Les Paul show. But Les Paul was able to develop, along with other contemporaries of his time, a circuit that was able to take separate audio signals coming in, manipulate them, and spit out several audio signals separately. His ability to work on the sound-on-sound methodology of multi-track recording, in addition to some of his experiments around audio circuitry for consoles, led us to the modern-day audio console. And it was not just vacuum tubes that these innovators were using, but it was also transistors. And in fact, one of the most famous audio circuits of all time is a piece of outboard equipment known as the URI 1176. The 1176 limiter was invented by Bill Putnam, who was also one of the innovators of the audio world. Putnam's 1176 used a field effect transistor. This transistor had a very unique sound in the way it manipulated electron flow, and to this day is still one of the most popular dynamic processors in the market. In fact, it's so popular that many companies have digitally synthesized it and created their version of a plug-in processor of the 1176. Of course, as I mentioned earlier, I think we'd be here all day and part of the night if we got stuck on just every single innovator at the time. So no doubt there were more innovators around this time that also contributed. Three I'd like to highlight, in addition to Putnam and Les Paul, are indeed Rein Namer. Now, Rein Namer was someone that was working for a long period of time with Les Paul. He was a Les Paul offsider. One day, Sherman Fairchild, who we will know in the future as the son of one of the inventors of IBM, was visiting with Les Paul and saw the work Namer was doing around audio circuitry. At this time, Sherman Fairchild's company, the Fairchild Corporation, did all sorts of amazing electronics, from really unique camera electronics all the way through to signal processing. And Sherman Fairchild contracted Namer to build him an audio processor. That audio processor came to life as the Fairchild 660 and the Fairchild 670, two of the most Indiana Jones-like circuits of the modern era. These signal processors are unique not only in their look, but also the way they operate and definitely the way they process audio. What's really cool about this innovation is that innovators of today that are still playing around with electronics can find a lot of inspiration. In fact, it was only a few decades after that that the famous George Massenburg put his patented parametric equalizer together. In the early 1970s, Massenburg, who is an engineer himself, was able to come up with a circuit design allowing us to basically circle in on select frequencies, amplify those frequencies, or indeed reduce the amplitude of those frequencies. The parametric equalizer, as opposed to the graphic equalizer, is something that is used in audio studios around the world. Its ability to allow engineers and musicians to be creative is second to none. And it's this innovation, this patent, this white paper that Massenburg submitted to the Audio Engineer Society in the early 1970s that allowed this to happen. No doubt graphic equalizers and other equalizers are used in fields such as broadcast, live sound, and of course audio-visual work. But it is that parametric equalizer that has such an amazing genesis from the earlier innovations of the Bell Lab 3's transistor, of Edison, of Bell. So really unique to draw a line from where we started to where we finish. As we move forward, it was not just these innovations in the United States, but all through Europe, there were innovations occurring as well. The unique thing about the European innovations is they all led themselves to legendary stories and products around the audio console. So let's have a look at three of what I think are those most exciting stories. We begin with EMI Studios, now known as Abbey Road. And the tech team at EMI Studios were the ones responsible for building almost exclusively all the audio circuitry being used. Now, that's pretty impressive because we have to acknowledge EMI Studios basically came to life in the 1920s. So by the time the 1950s arrived, some of these staff had 30 years experience with audio electronics and electronic circuitry. In fact, the famous Len Page and his team at EMI came up with the EMI Red 37 console. Now, this is a very famous console, not only for its looks, but also its sonic quality. The Red 37 console was an all vacuum tube console. So not only was the audio signal passing through vacuum tubes, but the way it operated, the way the direct current was distributed throughout the circuit was all done through vacuum tubes. And that is a really, really unique circuit to look back on today. From the 37, the EMI team then moved up and created the 67. In addition to that, they created the first transistorized console for EMI Abbey Road Studios, the famous TG mixer. Now, many people know the TG mixer, know the look of the TG mixer, acknowledge it as being one of the most famous consoles many of people's favorite records were mixed on. But the TG mixer took into consideration the way the actual engineer worked, the ergonomics of the engineer. If we look at the faders, they're very unique. They're on a slope. They are not the traditional linear faders we know today. And that is because the engineers at Abbey Road studied the operators, studied the way they worked, and created a circuit, not only transistor-based, but also an ergonomic outlay that enabled engineers to work most comfortably throughout their time. If that was not enough happening in the United Kingdom, an early gentleman by the name of Rupert Neve was also innovating with audio circuitry. Now, the name Neve is synonymous with microphone preamps and audio consoles. And throughout the last 60 years, Rupert Neve has been mastering the art of electronic circuits and has made some of the most famous sounding circuits known to modern day engineers. Neve started his career in the early 60s developing electronics for audio processing. His early attempts were mainly around vacuum tubes before he basically in the late 60s decided to go all transistorized. Rupert Neve's approach to console manufacturing was slightly different to the team at EMI. Rupert Neve's approach to console manufacturing and audio design was one of not only bespoke builds, but one that mainly took into consideration transistorized sound. That led Neve to create the next 2 decades of Rupert Neve circuitry through Neve Electronics before he decided to work on a really unique project, the Focusrite console. The Focusrite console is known as the Blue console. It's a console I've had the privilege of using at Ocean Way or parts of the circuit at Ocean Way in Los Angeles, and it's a console that has a very unique sonic footprint. Of course, only a few of these consoles were ever made. Most of the consoles had circuitry cut up and sold off as spare parts. So when we talk about the Indiana Jones items in the audio world, it's no doubt that the Focusrite Blue, or Focusrite console as it's known, is one of those items. Today, the Focusrite company is a very different company to what it initially started out as, which was a vision by Neve and his associates to continue the work of Neve Electronics. Of course, there was more innovation happening in the United Kingdom. And in the late 60s, there was a transistorized based company actually creating control products for pipe organs. A few years down the line, this company known as Solid State Logic saw the potential to start creating audio mixing consoles. The unique thing about the solid state logic audio mixing consoles is they added transistorized features not widely available by other manufacturers beforehand. That included machine control from the actual console. So no longer would an engineer have to turn around, hit stop, hit play, or arm a track. That could all be done from the console itself. Also, today we take for granted being able to change the way our audio circuits operate with sound. In the 1970s, that had to be done manually. So the SSL also looked at transistorized computer-based automation, being able to change circuits through time without human prompting. This feature of automation really changed the way a lot of engineers worked throughout the 70s, 80s, and 90s until we had the innovation of the modern day digital audio workstation. Without these innovations happening in both the United States and Europe, the world as we know it would not exist. And that is not a small comment to make, but it's a very accurate one. Indeed, without these innovations, subgenres of engineering, such as audio-visual application, such as modern-day broadcast, and of course live production, all would look very different. Not to be left out, Soundcraft, a Harman brand these days, was also innovating in the UK in the 1970s. And the Soundcraft team were actually able to create transistorized mixing consoles that were within flight cases. Now, the unique thing about this is we're talking about circuits that were very heavy, that were definitely not mobile at the time. They were set and forget type installs. The Soundcraft flight case enabled engineers and practitioners to take these audio circuits on the road, to make them mobile. And to this day, Soundcraft still has a really good history in creating mobile audio circuitry in terms of their audio mixing boards. These innovations around the transistor mainly, and also the beginnings of digital audio, have led us to where we are in contemporary times. We now have the functionality of large-scale format consoles in the 60s and 70s that will basically fit in the palm of our hands. In addition to that, the ability to operate these consoles has dropped significantly. The high learning curve, the years of studying under an engineer or attending formal education pathways are no longer necessary to actually purchase, operate, and get a good result out of this technology. It is the innovation of the Bell 3 with their transistor. It is the innovation before them of DeForest and his contemporaries that led us to where we are today. The ability to manipulate audio through electronic circuits and do it in such a way that is mobile, that is easy, and that is affordable. But that is only part of the audio story. Digital audio also is a massive part of what we do today. In fact, how audio is transmitted from location to location, how audio is captured and played back a lot of times now finds its beings in the digital realm. So how did this all happen? How did this come to be? And does it have any links to the innovators and innovation that we've looked at? Of course it does. So again, it comes back to not only the vacuum tube, but also the transistor. Vacuum tubes and transistors helped engineers and inventors create digital audio systems as early as about 100 years ago. Now, these digital audio systems were very different to the ones we know today, but they did in principle exist. And the unique thing about that is they existed for some of the most demanding applications: encoding communications, again, telecommunications, and where necessary, short logical processing. So the unique thing about this is that without the innovation of the vacuum tubes, Fleming, DeForest, and contemporaries, without the innovation of the modern transistor, the Bell 3, we would not be where we are today. An early digital audio system was known as the Sig Sally. This system was manufactured in the United States of America and installed in certain locations in the USA, as well as certain locations in the United Kingdom. It was used for coded discussions between leaders of both countries leading up to and during the World War II period of the 1940s, and was decommissioned in the United Kingdom not long after that. Now, the unique thing about the Sig Sally system is, yes, it was encoding audio, but it was doing it with vacuum tubes. Remember, transistors were not invented until the 1940s. So because of this, it had some unique characteristics. It was huge. It was physically massive. It actually needed its own large room with a lot of ventilation. In addition to that, it was using hundreds, if not thousands, of vacuum tubes at times. Not all these tubes were going to last. So there was the process of a tube breaking down, an engineer finding the fault, replacing the tube, and then getting the system up again. Really unique stuff. In fact, when we talk about power required, the vacuum tubes needed up to 30,000 watts to power the whole Sig Sally system. That is an extreme amount of power. And as we move forward, it is the Sig Sally system built on vacuum tubes that led us into the world of digital audio. From there, some very unique innovations were made. It was not just being able to take electron flow, convert it, and then transmit it. There had to be error checking along the way. There had to be a way to adopt this electron flow and then store it as a digital word. And how did that happen? Well, that story is probably a webinar and a half on its own. However, it was key innovators such as Claude Shannon and the like, a number of people contributing to the IEEE body of work, that were able to come up with pulse code modulation, that were able to come up with error checking, that were able to put together a range of solutions around this conversion process to enable us to go from electron flow to actual digital audio, which is pretty cool. The 1950s actually saw audio circuitry starting to use some of this knowledge in the way it worked. Indeed, Bell Laboratories created the T1 carrier. Again, telecommunications enabled us to take analog signal, convert it in such a way that it was taking into consideration pulse code modulation and other innovations by Shannon and his contemporaries, and put it together and transmit it. Not only was it Bell Laboratories, but also other companies such as Texas Instruments that were able to put together components and circuitry that allowed us to really make processing digital audio a realistic ability of engineers and telecommunications applications worldwide. As the 1960s came to a close, we started to see digital signal processing and indeed the transistor take on new life. We saw things such as logic chips, operational amplifiers, actually integrated circuits as well, change the way transistors worked, change the way we used transistors to design circuits. No longer were we implementing 40 or 50 transistors on a circuit, but we would implement one component that could potentially have 100, 200, or in the case of the Intel Pentium, thousands, if not millions of transistors within the one chip. Once that happened, the amount of processing required to encode electron flow into ones and zeros was now achievable on a mass scale. Although we're now in the 1960s, it's vital to know that the Sig Sally system and a lot of the circuitry around it was still secret and was not actually lodged for patents until the late 1970s. So the commercial world was actually innovating totally separate to what the government was doing with its Defense Department and its use of the Sig Sally. Really unique, and another great example that shows us that things happen in parallel that are sometimes just not connected to each other. As the 1960s drew to an end, we started to see the ability to manipulate digital audio mature. Things such as the FFT algorithm came to be, allowing us to take snapshots of audio, process that audio, and do it in such a way where we're not using the massively long word lengths that were associated with it. By using protocols and filters such as the FFT, along with using computer circuits that were able to do the work of hundreds, thousands, if not millions of transistors, processing digital audio became a reality. And when we say processing, we say actually changing the way that audio is recorded, changing how it sounds, adding new characteristics to it, or removing some of those characteristics. Vital to the work of removing characteristics and a lot of echo cancellation was M. Mohan Sondhi in the late 60s. M. Mohan Sondhi's work, which can be referenced in the IEEE archives, really went into the depths of echo cancellation. Now, at the time, a lot of technology available to Sondhi was all basic transistorized. So his ability to echo cancel a 10-second audio recording took 24 hours to process, a whole day. We can now do that processing in real time. And in the world of audio-visual communication, we see those kind of features being used on a very regular basis. But it was not just Sondhi on his own. It was also contemporaries at the time working on creative ways to make this happen. Indeed, Francis Lee and Dr. Barry Blesser were working on a way to basically delay audio. And one of the highlights of my career was being able to speak to Dr. Barry Blesser not long ago and hear his story of basically anything is possible, just give it a go. And he was able to manipulate audio coming into a circuit, delay it, and then spit it back out. This was the very, very early innovations of audio delay systems. In fact, some of this circuitry was used by companies such as the famous Gotham Audio in New York to create large PA systems. And indeed, it's Barry Blesser's innovations that led to the Gotham Audio Lexicon T101. And of course, today we know Lexicon to be a world famous brand under the Harman banner, a brand that's doing digital signal processing and amplification for the automotive world, for the cinema world, and of course, for the recording world. In fact, the Lexicon PCM70 is one of my favorite products of all time. In addition to that, Francis Lee's work also contributed to such famous units as the EMT250, a wonderful digital reverb unit. But it was not just effects that were benefiting from this. The creative process as a whole was really reaping the rewards of innovation, of transistors, of earlier amplification. Indeed, two Australians were able to put together a Fairlight system that was able to reproduce audio on a screen, but also assign it to keys. It was one of the world's first samplers, and the Fairlight CMI product is known globally in terms of changing the way modern music was created and how creativity was pushed to new lengths. Very cool stuff. Outside of that, it was not just digital audio, but the protocols and how to transmit audio that also changed over the years. So as we finish today's webinar, we're going to have a quick look at the protocols and indeed how audio goes from one place to another. This is not something that we think about a lot when we're in the recording studio, but it is there. It's not something we think a lot when we're in the live environment, but again, it is there. It's something that we really do focus on quite heavily in the world of broadcast and of course audio visual. We're ensuring that the protocols are all matched, that the audio is all talking to each other, that all our ticks are lining up, that our master word clock is doing its job, that our other components are slaving correctly. So if I haven't lost you so far, let's get into the final part of today's presentation, which is digital audio protocols. So the unique thing about digital audio protocols is that there are many of them, and that can be a confusing thing at times. However, digital audio protocols basically allow two digital pieces of equipment to talk to each other, to pass audio to each other or through a switch, whether we're doing networked AV or indeed AV over IP. There are many digital audio protocols out there, and today's webinar is not to focus on any one, but to give you a brief overview of some of the most popular over time and how they came to be. So in the early 1990s, one of my favorites, MADI, multi-audio digital, actually we'll come back to what that stands for, but MADI was able to put, the AES community, the Audio Engineering Society in New York, was able to put together a protocol, AES 10, that basically had MADI, multiple audio digitally transmitting across networks, across devices. Now, the unique thing about MADI is that it was able to transmit initially 56 channels of audio. Now, what's unique about that is that by having this protocol, by adhering to this standard, we now no longer needed the copper conductors of earlier times. We now no longer needed the thick multi-core connectors. What we could now do is transmit audio digitally. So we no longer had to worry about encoding audio, recording audio digitally, and then turning it back into electron flow to transmit it. We could now transmit it digitally. And of course, there were innovations before this, but MADI is the first standard protocol that we were using on a regular basis. Outside of that, there were other protocols privately developed over the next 10 to 15 years, one of which was Harman's BlueLink. The unique thing about Harman's BlueLink is it actually offered up to 256 channels. So you could now throw a lot more audio across a much wider bandwidth than what was previously available. This was a really unique product feature that was applied in a number of the Harman products and still is to today. A really, really cool way to transmit audio. Outside of that, we've got Dante. Dante was an Australian innovation, and the unique thing about Dante is where protocols and standards such as BlueLink would require networked audio, so audio going from point A to point B destination, Dante was actually able to throw audio through network switches. So you could now throw it to multiple places at different times and control that. Very unique, and it's something that's adopted today as a protocol by many manufacturers globally. It's something that a lot of engineers are trained in, and it's a unique solution to the networked audio discussion. Now, we look at protocols, we look at digital audio. Where do they actually meet? Is there a way for all this technology to meet? Well, of course there is. If there was no way for them to meet, we actually wouldn't need them. And the way for them to meet was the actual circuitry. Now, a lot of audio circuitry started to have analog to digital and digital to analog converters in them. But in addition to that, they started doing the digital signal processing on board, whether that was echo cancellation, whether that was dynamic processing, or whether that was something as simple as routing. Now, there are a lot of DSP, digital signal processing options on the market today, all of them really good to some extent. I'm going to focus on the BSS range. And the unique thing about BSS is it is another one of those United Kingdom European inventions. The company was started in the late 70s on the back of transistorized circuitry. By the early 2000s, it was a Harman brand, and it was morphed into a digital signal processing brand. Indeed, the BSS range of DSP processors are known globally and one of the industry's most welcomed. The BSS digital signal processors take into consideration not only Harman's BlueLink, but also other protocols such as Dante, such as AES-EBU, and even SPDIF in some cases, to transmit audio from one location to another, be that point to point or be that over a wide network. The way these circuits and these solutions operate have indeed changed the way we as an industry work, be it in recording studios, be it in broadcast, live productions, or even audio-visual solutions. Being able to take the early innovations of Bell, DeForest, the Bell 3, and others, and put that all into solutions means that the microphones, the magnetic recorders, the digital recorders, and the speakers we use on a regular basis, daily, if not hourly, are all benefiting our lives in a way that was not known 50, 60, 70 years ago. What I find most amazing about this innovation is that it continues today. And perhaps the most inspiring thing about looking back is being able to then look forward. If we look at the timeline of innovation, we see that these creations, these steps forward in technology happened at a regular pace. There was no one period where innovation was at its maximum. And I find that really inspiring, because I believe that today, as we move forward, the operators of audio equipment are the ones best equipped, the ones actually using audio every day are best equipped to say, we can go this way, we can go that way. Let's try doing it this way. Let's come up with a circuit. Let's come up with an algorithm. Let's come up with a piece of software, a protocol, or even a standard that allows us to do what we do better. Whether that is transmitting audio from point A to B, whether that is recording audio, whether that is transducing audio, it's all possible, and it's all possible to improve on. All we have to do is be aware of our surroundings, be aware of the journey to date, and constantly work together to innovate. Having said that, that's about the end of the slide. So if there's anyone still online, I thank you. And to Laura, thanks so much for hosting the webinar.
Thank you. Can you see me? Am I back on?
I absolutely can. I hope I didn't put you to sleep there.
Not at all. That was wonderful. Thank you. I don't see
Thank
any
you.
questions in the Q&A. We'll just give it a minute if anybody had something that they wanted to submit. Otherwise, Peter, did you want to share your contact information in case somebody wanted to email you directly?
Absolutely, Laura. So my contact information should be in one of the slides. It's peter.moses, M-O-S-E-S, @harman.com. A quick Google search will bring up my contact details, and I am more than willing to discuss this at any opportunity I get. Audio innovation and the practice of audio engineering is something that I'm really passionate about, and being able to help that discussion move forward is time well spent as far as I'm concerned.
Wonderful. Thank you so much, Peter. This was great. And just a reminder to everybody, it was recorded. So if you have any interest in sharing it with somebody from your company or team, it will be posted out on our brand channels in about 3 days, along with all of the other recorded sessions. And if you want to view our upcoming calendar, go to pro.harman.com. You can see the full calendar of upcoming sessions there. Thanks so much and have a great rest of your day. Thanks, Peter.
Thank you. Thanks, Laura. Thank you.
Bye.